Log on, tune in, find out. Another good idea from Cambridge.
Two talks will be on nifty covariate adaptive designs, and you'll hear details. Then we'll have our tea break, and then we'll continue in a slightly different spirit with Peter Tart. And in the end, we have a discussant who is already sharpening her knives. It should become a good session, yeah? So our first speaker is Yuan from MD Anderson Cancer Center, who will tell us about adaptive reassessment and randomization. Please.
Thank you. Thanks, Peter, for inviting me, and thanks for sticking around toward the end of the workshop. But from all the information I've heard, it's going to be a really fun and dynamic and interesting session, so stick to the end. Not my talk, but the end of the session. So this is a fairly recent work. We started to collaborate, and you know the two of the people who just talked at the end of the author list, and Lorenzo, he used to be a student from Italy, and then did a postdoc at MD Anderson and Harvard, and now is becoming assistant professor, starting his wonderful and exciting career at Dana-Farber. So I thought hard about the name, because this is trying to, taking the torch, or following up the wonderful works by the Battle and the SPY 1 and SPY 2, and I thought it must be something interesting about biomarker adaptive designs. It's all related to military, so it must be powerful. And I was thinking, maybe my name should also be related to military, and this is what the best I could come up. Arm, weapons. So with two R's, I was trying to get army, but failed. But anyway, what this is just a combination of three really popular words in adaptive design field: adaptive reassessment, if you are into the continual reassessment thing, it's in the same spirit, and randomization. I put R and M there so that I get an M in the end. So with all these the hypes and the details and the complications from the recent adaptive designs that are using response adaptive randomization, the underlying assumption is there exist subgroups that differentially respond to treatments. So that to me, that's the key assumption to really warrant a trial that's based on response adaptive randomizations. If you don't have patient subpopulations that would respond differently to different treatments, then why would you want to adaptively randomize? So that's really, to me, the key, and I will use DRT to represent differentially respond to treatments throughout. So biomarker adaptive randomized trials, they are in the same spirit, except that the subgroups are now defined based on certain criteria related to biomarkers, the biomarkers being either genes or proteins. So, but the main thing is the same. So you need to have biomarker subgroups that DRT, differentially respond. So these I'm going to review just briefly each of the two pioneering biomarker trials that have been related to MD Anderson. The first one, and you have heard talks in the early programs, so I don't have to go into the details. So the first one is Battle, and then Jack presented a nice one a couple of days ago. And the underlying assumption is that there's biomarker groups, and the adaptive randomization is done within each predefined biomarker groups, and those biomarker groups are based on different types of mutations. And this plot is just stolen from their paper, which just appeared this year. So the concept is you predefine certain biomarker groups, and you have a list of candidate treatments. These treatments, at the best current knowledge, are believed to target certain biomarkers that you just defined, and therefore each groups would respond differentially to these treatments. And since we are not sure before we see any data, we want to do a trial to see if that's the case. If it indeed is the case, adaptive randomization would put more patients to put the best treatment to those patients that respond, and then for those who do not respond to that treatment, they would get low chance to be randomized to that arm. So this is again the centralized, the underlying assumption is the DRT, the differential response. And so I just found this vintage picture of Jack, which looks really nice, and it's actually on your website, right? So the so the second one is the SPY trial. It's the second SPY now, I-SPY 2. Again, so this is just in no ways this is a full description of the I-SPY 2, but this is in their early paper. Idea is the same. In this diagram, the idea is to first predefine biomarker groups that divide patients into HER2 positive or HER2 negative. So they do that up front, and they and look at the expression of HER2. If it's high, then patients go to this group. If it's low, go to this group, and they are randomized afterwards. So again, the two things: the patient definition of biomarker groups are fixed and predefined before the trial, and then they are fixed throughout the trial. And during the trial, the treatments are adaptively randomized. So there are two people I think are critically related to this trial. First is, of course, Don Barry. And then I start to have trouble. The second person that's critically relevant is Kyle Watson, who gave a talk a couple of days ago. I couldn't find a picture online. And this guy is called Kyle Watson. That's what Google gave me. So, and I forgot to take a picture while he's here. He left. But he's doing something, right? It looks like surgical, but. So anyway, again, so I think I hope at this point I have get my point crossed. A common theme at the most current front of biomarker adaptive trials is that the groups that define different subpopulations are fixed prior to the trial, and they don't change. So why is that a bad thing? Because we all know science is imperfect, so we are always learning. Those definitions of biomarker groups are based on the current knowledge, and as actually some of the analysis from battle trials revealed, in certain cases, the groups that you think that would respond differentially to treatments, they don't. So why bother with? And it's kind of waste. At the end, especially at the end of the trial, if you see that, then you say, why do I do this? Right? So why don't I change that definition and then make a better classification of my biomarker groups? So these are the things I consider that can be improved. And that's the motivation. And the last point is basically something we wanted to do and haven't figured out how to do it yet. So a lot of these biomarker groups are defined based on a single gene or protein being up or down. But if you know a little bit of biology or system biology, you know that the disease like cancer are usually caused by a very complicated cascade of events. It's not just caused by one gene or one protein doing something unusual. It usually involves a pathway. So that's something we have been thinking about, but so far still, I guess those works are still on the sketch papers. So this is just, I purposefully didn't fit everything into the screen, so don't try to find what's going on here. This is just trying to convey a hypothetical example where I have 3 treatments, and these 3 treatments are green, red, and black. And I'm plotting the probability of response being a binary response, whatever that is. The probability of that response being high means it's good, you're responding to the drug. And I'm plotting this against the values of a hypothetical biomarker. And I have two biomarkers. I'm fixing the second biomarker at the different values, and that value keeps increasing. So this is a sequence of scatter plots between the the probability of response versus the first biomarker, while the second biomarker values increase. Okay. So what you can see is, if you just ignore the black line for the moment, if you look at the order of the green and red, the greens and red the green was on top in the beginning and gradually comes down, and red gradually goes up. And toward the end, I'm going to show the full picture where red eventually is clearly on top. So this means the message is that if your biomarker group is based on the definition of the first biomarker, it's not going to do anything in your trial to differentiate the patient response, because it doesn't matter how the first biomarker changes, the order of the therapeutic effects from these three treatments is the same. The green one for a given second biomarker value. So it doesn't matter how you define your biomarker groups based on the first marker. But if you define that based on a second marker, then it starts to get interesting. In certain cases, you will see a subpopulation that would prefer the green treatment because, for example, here the green has more probability of response. In other cases, when red is on top, then you will see that those patients would prefer the red treatment. So that's the idea of this. And we're going to run simulations for these scenarios. So again, what we propose is it's very simple. Just try to adaptively reassess your biomarker groups. You can do something in the beginning based on the best knowledge of science, but once you start to recruit patients and observe their data and response, that's information you could use to help your design, especially help you to redefine the biomarker groups that would differentially respond to the treatments. So that's the idea. And this is just a proposed scheme that how we would run such a trial. It's very similar to the battle and the I-SPY 2, except that here in the end, but it always starts patient enrollment and then using the best technology, current technology, science knowledge that you would define, for example, 3 marker groups. MG means marker groups, and then you would have, I call it a running phase. This is, I guess, a terminology used a lot in adaptive randomization trials. A running phase means that you want to avoid variabilities in the beginning by doing adaptive procedure because of the small sample size. So what you do in the beginning, you actually equal randomized patients just to have a data collection process where you can do some meaningful inference afterwards. And then immediately after the running phase, once you observe data and response from the patients that have been equally randomized, you can do a biomarker group reassessment. And you can run some model to redefine how you would say the MGs, the marker groups. And there you could find a different set of marker groups and even different number of marker groups. And afterwards, it's pretty much the same thing in in cycles. So you would adaptively randomize your treatments to these newly defined marker groups. And once you observe new data, you reassess your marker groups and go back. You get a new set of marker groups and adaptively randomize the next set of patients. This part could either be fully sequential, meaning you could update every time there's a new patient is enrolled, or you could update every cohort of patients. But those are the details we would not go into at this point. So it has a running phase and the arm. So we actually have a trial that we're considering, this is a very special case. So there's a PI at the MD Anderson, and she's a breast cancer oncologist. She currently has patients that have been treated by neoadjuvant systemic therapy, NST, and surgery. And these patients have their biopsy done, so their biomarkers, the protein expressions, have been measured. And for these patients, their prognosis are not good from the frontline therapy. Therefore, they are considering the second line therapy, which are these biomarker treatments. Actually, there are 3 types of inhibitors that target 3 different pathways. And these patients will be divided into 4 different marker groups based on, again, the current knowledge, based on their BRCA mutation, their PI3K pathway activation, and cell cycle pathway activation. And then the 4th one, I guess, is negative on both, on all 3. So they call this an umbrella protocol because you can treat each of the marker group as a separate phase 2 trial and randomize. But the entire protocol says how we're going to do adaptive randomization for all 3 marker groups and with 3 treatments. So that's the trial we have in hand. And there's just some special thing about the measurement of the proteins, which I would touch upon, because I think it would be nice to convey this new technology to you. And it's called RPPA. It's called reverse phase protein arrays. It's a specific type of tissue array for measuring protein expressions. And unlike the usual traditional classical microarrays, which put genes or protein probes on the glass slide, this type of technology put patient samples which contain the reservoir of the proteins on the slide. And they hybridize each slide against the one antibody that represents a protein. So at the moment, they could do 2,000 patient samples on one slide. And if they use 50 of the slides, then they could measure 50 different proteins. So it is a reverse order as the traditional microarray, which put genes or protein on the slides, and patient samples is the thing they hybridize against. But the nice thing to statisticians with this type of design is after the treatment, your data set has a sample size of 2,000, and the number of proteins is only, for example, 50. Now you have the n greater than p problem. So we heard a lot about p greater than n for genomics, but this one is very nice where you have large sample size. And for this type of thing, it's very good and helpful if you want to do pathway or network analysis, because the sample size is reasonably large. So for this trial, they had 255 patients, and their protein expression are measured for 14 proteins, and these proteins are selected from these 2 pathways. So our data set would eventually, we actually have it. We have a data set of 250, that's the n, and then p is 40. So this is the technical slide where we, how we would run this trial and fit the models. So suppose we're going to randomize 250 patients at the end. So that's our capital N. And we use xi to denote the biomarker expression profile for the patient I. So xi is actually a vector of 40 numbers in that case. And then ti would be the treatment selection 1, 2, 3. We have 3 different candidate treatments for patient I, and yi would be the binary response variable, yes or no. So again, as the scheme indicated, we would have a running phase where we equal randomize a small subset of the patients, that's the little n. Once we do that, we can fit a model, and And in this case, we'll fit a Bayesian model because we want to do prediction sequentially, and that's perhaps the easier way to do it. So this Bayesian model would have a sampling model and priors. And we will fit this model using the current observed data for all the little n patients that have gone through the running period. Now the adaptation starts from patient n plus 1. For patient n plus 1, we would compute a posterior predicted probability of q n plus 1 t, and that's essentially the probability of the next patient, which is n plus 1 patient, have a response given the observed data from the running period and the observed protein expression profile for the n plus 1 patient and the proposed treatment allocation. So this can be calculated as usual by integrating out the model parameter theta based on the posterior from the previous data. So that's a standard procedure. And for each of the t equals 1 to 3, so we have 3 treatments, we would get the probability of q. And then we can you can just brutally use the q as your adaptive randomization probability to carry on. And that would be the probability to randomize the n plus 1 patient. And as many of you would argue that using q is too brutal, you could use something different like q to the lambda's power, lambda being 1 square root. That's perhaps a better one, but it's not the focus of this talk. So I just say it's a function of q. And indeed, in our simulation, the function is basically identical function. It's q. But that's how you would randomize n plus 1 patient, and you would observe the response from that patient. And you could do this now for the n plus 2 patient, given the observed data from the previous n plus 1 patient. So the practical considerations such as delayed response, those kind of things can be tackled by, for example, using cohorts or doing some predictions. But this is the main idea of how you would carry out this technically. So of course, I haven't told you anything about our sampling model yet, because those are the details and they are not important, right? But I'll try to give you some examples and candidates. So the sampling model says what's the probability of yi equals 1 given the covariate and the treatment and the other model parameters. So there are two choices that you can think of. First, you can think of this as a regression problem and just treat different covariates as biomarkers as covariates, and you can do a variable selection. That's one choice you can think of. And the second one is I don't want to deal with the variable selection part, especially what if I don't have reverse phase protein arrays, which only gives me 50 proteins? What if I have microarrays in which I would have 20,000 genes? That would become a research topic on its own. So you can do this another area of a statistical research called dimension reduction. We just use the simple one in our simulation principal component analysis, which reduces your dimension of X space into a subspace Cx, and dimension of Cx is much smaller than X. So in our case, we assume we have, for example, the first 5 principles of the biomarker matrix. So again, for the sake of this talk, we took choice 2, but it's not the only choice. So this is the full model. So we have the space of the biomarkers, and we want to find the subgroups that would differentially respond. So those subgroups are essentially defined by a partition, and in this case, we propose a model that would define a random partition, and let's call that pi. So basically, pi is a sequence of subsets of X, and these B's form a partition of X, means they are disjoint, and the union of all the B's equals X. Suppose we know the partition of the X space, then we will define the probability of response, which are the theta, given the treatment J and that partition subset. So these are our prior for the true probability of response, and they follow basically, once you know the partition, they are I, D, beta distributed. This is the model. If you know if you observe the biomarker measurements and you know your treatment allocation and you know how to partition it, and of course you know your theta, the mean of response, then what you observe is basically 1 or 0, and that's a Bernoulli random variable, and the mean is again theta. It's indexed by J, the J's treatment selection, and M of X. M of X basically means that the subset in this partition where this Xi would fall into, based on whatever the partition rule is. So that's the entire model, and with that we can run. So in this case, turns out everything is in closed form. There's no MCMC. You can just calculate everything by just punching in the formulas in the end. So there's just a little constraint. So sometimes we run into really small subsets, meaning like you could probably perfectly define subsets where it differentially responds, and such subset would only contain one patient. So that we don't want to run into. So we want to contain some size of the partition subsets, and that's sample size. So the number of elements in B has to be greater than 30 patients. Otherwise, it becomes too small. So again, everything here is clear except how are we going to run this random partition. So this is just a simple hypothetical example to give to illustrate the priors on the partition. Choose a patient I, and suppose the observed biomarker measurements are vectors is indexed by Xi, and with probability Pi. I here is the number of biomarkers. So let's say we have 5 biomarkers. They are the 5 principal components. So with probability Pi, you pick one biomarker. And with another probability Q, you split the space of the biomarker X by cutting the Xi in the middle. In this case, I chose X2, and this is the median of X2. I cut it. The whole space become 2 subspace. So those are my first cut. Now I have 2 subsets. I do the same. With probability Pi, I pick a biomarker. With probability Q, I split it. So in this subset, I picked X2 again, and I split it. In this subset, I picked X1, and I split X1 in the middle. Just keep doing this for the 3rd time, and so this is what we get in the end. Since these are with probability, so sometimes I don't split. Okay, so it's not always I'm going to split. And just repeat 3 times, and turns out if you do this, repeat 3 times, you end up with something like 50,000 different partitions. And we thought that's large enough, and at least for this simulation purpose, and that's when we stopped. So you can easily calculate the prior probability of such a partition. And so we have 50,000-ish of these partitions, and each one you can calculate the probabilities, and that's the prior. So now let's look at the simulation. Again, I assume we have 5 principal components. They are X1 to X5. And just to keep things simple, we only assume X2 is the relevant biomarker, means the patients in X2, they would differentially respond to treatment. So again, that's the full picture of the previous one I cut off. X1 is the horizontal axis, and the probability of response is the vertical one. And as X1 goes from -1 to 1, you see all treatment response goes up, but the order maintains. So it doesn't matter which treatment you use for the different values of x1, they would just have the same order. But when you change the second biomarker, you would see at the end. So here, the green is on top, and then as you keep going, here they cross, and here the red is on top. But in any event, they are better than the third treatment, which is the black. Okay, so that's our scenario. Thank you. So for, I'm just going to pick one scenario. So there are 20 of them. You can simulate data using either one of them. And just randomly pick the number 18. In number 18, we have 3 treatment, again represented by the 3 colored lines. And treatment 1 is the red one, which is the best. Green is the third one, and the black is the second one. So this is the choose. And then x2, the second biomarker value, is fixed at the 0.8 in this true scenario. So we ran small simulations. So we ran 100 simulated trials under this scenario based on our procedure. And we used the sample size. So the first 100 patients are run in. So they are equally randomized. And after that, we started adapt. And this is what happens if you are at 150 patient. And this is these histograms shows you the difference between the posterior predictive probability for the 151 patient. If that patient, I think in this case that woman, because this breast cancer, were treated by treatment 1 versus minus the posterior predictive probability of that patient if she were treated by treatment number 2. And these are the probabilities of response. So the higher the better. And the truth is that number 1 is red, is the best. Number 2 is the second best, and number 3, the black, is the worst. So you see the different, this is the histogram of the difference out of the 100 simulated trials. And you should expect that this histogram is skewed to the right, meaning there are more positive differences, meaning the patient is more likely to be randomized to treatment number 1 than number 2. And that difference is probably smaller than between 1 and 3, because 3 is the green, so 3 is slightly better than black, and that seems to be the case. So what happens when it goes to 200 patients? So I'll just do it back and forth a couple of times, 150, and if you pay attention to the peak, 150, 200, 150, 200, it pushes to the right, right? So means as you have more and more patients, the evidence becomes stronger, and the histogram is telling us actually 1 is indeed better than 2. What happens when we push to 250? So perhaps the peak doesn't move anymore, but certainly the variability start to tighten up. So the posterior, this is not really the posterior, but you have less variabilities in your predictions. So this is what it's telling us. So that's one summary, and this is just to show how the trial would have been carried out had we chose this approach. Again, for the first 100 patients, these are the patient index. First 100, they are equally randomized, so there's no adaptation. Adaptation started at the 101 patient. But and the true scenario is that the red treatment is the best. Therefore, it should, once you start adapt, get higher posterior probabilities. So since our scenarios and setup is so simple, we immediately see, starting from the 100th patient, the red is already on top. So we probably should have started adapt earlier. That's the message. But the interesting thing to see is actually at the bottom. So red is always on top, which makes sense. But in the beginning, the black is actually on top of the green, which is untrue. But As you can see, as you recruit more and more patients, they start to cross, and at the end, the black dropped, becomes the worst. So that's the learning part of this. So another message from this is, and this is 300 patients, so you probably need some time. If you want to do this, you probably need to be patient and wait until things to settle down instead of jump onto conclusion too early. But that's when and we should stop. That's another thing we are still thinking. So I don't have much left. Again, the message here is you have to believe that for this particular trial you're trying to design using this type of approach. The assumption is that there's a DRT group. Patient would differentially respond. Otherwise, it makes no sense to do it. But once you believe in that, then you know there's always error in our science or unknowns. So your definition of biomarker groups may not be the best for these patients, and for that you would be willing to learn and adapt to redefine your biomarker groups. So that's the take-home message from this. And the next speaker will continue and give you an even better illustration of this type of ideas. Thank you.
Thank you. You were awfully quiet. Does it mean you kept your questions to the end? Please.
I'm trying to relate parts of the talk together. I'm a bit puzzled because so you described this complicated scenario and changing the subgroup definition. And somewhere in there that looked to be a model with a parameter theta. But then later you talked about using CART, which is not really model based, and seemed to be a different approach to that. And then your last simulations, you were showing, I thought it was just one group of patients. There weren't any subgroups, were there? So what there? The other subgroups? You're showing that one treatment is doing better than the other and moving people that way, but you're not doing it differentially for some patients or others. Or can you explain?
So what we should, we actually have subgroups. They are just not presented, or we didn't have time to summarize, to be honest. But here I forgot to mention. So that's probably what you're asking. Here I fixed actually the informative biomarker. Let's call that. That would differentiate. Dictate a differential response, which is the biomarker number 2, and that's for patient N, right? And with these three lines, the second biomarker value is fixed at 0.8, and that's this scenario. And therefore, you would see this type of nice thing. But ideally, with the random partition, every time you'll get a different biomarker groups for every single patient, depending on their values, right?
So I'm wondering about sample size. You've got 300 subjects all in that particular case.
Oh, this is not a real case. This is just to show you.
I know, but when you've got that one thing tied down, you can say with 300 subjects, I can see that I need to do this rather than that.
Exactly.
So you need another 300 subjects with a different scenario, and you're choosing which scenario. What's the real sample size in your study? Is it millions?
So so there's one thing we could do is to randomly generate, and actually we did that. We just didn't present the plots, right? We could randomly generate these X values for the second biomarker groups, biomarker proteins, and they would be in different categories, right?
And so you end up saying treatment 1 is better for these people and
exactly.
treatment 2 is better for those.
Exactly.
That's a much more delicate.
Exactly.
That's fine.
Right.
Yeah, I mean, so I was puzzled by the same thing. It says treatment 1 is the most effective, but almost your first slide said we assume that we want different treatments for different groups of people.
So this is one snapshot of the case where treatment 1 is the best when X2 is fixed at 0.8.
For a particular patient, right?
For a particular patient. If X2 changes from a different patient, then the red could be at the bottom. Right. Sorry, I didn't show that.
If I may, just to clarify what that figure is telling us is that if you happen to have the initial sample size of 100 to do the initial biomarker group sort of grouping, and if you have 110 patients coming with that,
you would immediately
that biomarker values. that the red, green, and black shows the probability of that next patient getting into different groups. And then when n is 101, it shows the probability of 102nd patient with the same covariate value. What is their probability assigned to a 1, 2, 3? It's just an illustration, right?
Well, the question
Yes,
I
thank
started with was how do you model that whole multivariate dependence on all the biomarkers? And is there a model, or is it just a CART algorithm for?
It is a model, so it's a
Right. Okay. But I don't think
The
we saw it.
Bayesian card is a model.
right. It's a model.
So how many biomarkers in the simulation you
5.
So in the simulation study,
Mm-hmm.
so you have marker 1 is prognostic, marker 2 is
Marker 2 is prognostic.
no, marker 1 is
In that sense, yes. It's
marker
not
1 is
differential.
prognostic,
Right.
marker 2 is predictive,
Right.
and the 3 to 5 are nothing,
Right.
and then total sample size is 300.
Right. And so along another thing I forgot to point out is along this line, x2 is fixed, right? So the second biomarker is fixed at 0.8, and the others are randomly selected. So those values are actually different. So it's not truly the same patient, but it's a bunch of patients, but these patients happen to have the same x2. I just want to illustrate when that's the case, the learning process. We could have randomly generate all the x's, but then this thing would be jumping all over the places, and you wouldn't be able to see the pattern. But that's ideal, and practically that's what's going on.
Well, that's what you want.
Exactly. Exactly.
I think
Steve?
we just can't see it. Sorry.
Steve?
How sure are you that the green and black lines are different? I mean, if you had more than 300 patients, the black line could wobble up again, for all I know.
Sorry?
How sure are you the green and black lines will remain different after 300 patients?
We would have simulated more, right?
Well, I mean, because if you started the simulation earlier than 100, then you would have had a better prediction, but they wobble quite a bit in the beginning. At 250, you can't tell what. 225, they're identical again. So you said to wait.
And I think for this case, so that it's a little bit misleading in this case. Well, it's not entirely, but you notice that because the randomization probabilities for these green and the black are low, so which implies they actually get fewer patients, sample size are smaller, and therefore the learning takes more time. So that's my intuition when I look at it. So that's why when you have to hit 300, and then maybe they would cross again, but you know.
But since you know that the red's better, then why don't you spend your time learning about green and black?
I'm sorry?
Since you know red is better early on, why don't you spend time learning about green and black at some point? Because you're randomizing only very few patients to those groups. Your error will be large. It's going to be hard to tell them apart.
But in reality, I don't know which one is better, right?
But actually, he doesn't. You don't spend time on
I don't, it's
learning
just,
about.
right. Sorry. It's just what model spits out. I don't specifically try hard to learn the green and black. It's just what this model is telling us based on observed data. Right?
Probably what Steve is saying that you should have a stopping rule of utility and just cut them off, the green and black, and just go with
You could, you could threshold them and then say that's it. I'm not gonna waste more patients. But
Jeremy?
So at the end of a study, do you have a partition that you're going to hand out to somebody? Because it's sort of unclear what this partition is. It's moving around, it's a distribution, what is it?
very good point. I think so. All these things at the end. So we talk about personalized medicine or targeted therapy, right? What is it? After the trial, this type of trial, your conclusion is going to be different from conventional trial where you say, oh, treatment 1 is the winner, you start, and then FDA, please approve this and use it for all the patients. You can't do that. After this type of trial, you'll say, whenever a new patient comes in, I'm going to measure the relevant biomarkers and find out which group this patient is in, and then I'm going to use the corresponding one, right?
But I think Jeremy's question was, where do the groups come from? The groups are...
Is there a fixed grouping?
No,
at the end?
it's. I think my current idea is that this at the end you need a software that will continue the learning, because disease also evolve over time. You can't just say, oh, that's it, I've learned enough and this I'm going to fix that rule. and whatever happens in the future, I'm gonna define the marker groups. I would put this out there as something like a standard tool that physician would use, and that's what they're gonna choose. So I don't know if that addresses that.
Brahma, you can.
Okay, I can.
Any other comments? Brahma is a discussant in the end, so we'll just ask you to keep your questions. So then let's thank Yuan again. Thank you.